Well, first, I just want to thank the organizers for the opportunity to talk about dimer models. And yeah, so I'll to start with today, kind of the history of where they appear in algebra, and then tomorrow go into more geometric ideas from dimer models, and then on Wednesday talk about other surfaces, higher genus surfaces, and then on Friday talk about cluster algebras and categories with dimer models. Okay, so yeah. So throughout the talks, K will be in algebraically closed field, and there are times when some of the results will depend on K being uncountable. We denote the vertices and arrows of a quiver by Q0 and Q1, and the vertex idempotence by EI. And modules are usually meant as left modules, and path concatenation is read right to left. Okay, so let sigma be a connected compact surface. Forgot to say oriented. A dimer quiver on sigma is a quiver whose underlying graph embeds in sigma such that each connected component of sigma minus the graph is simply connected and bounded by an oriented cycle called a unit cycle. So dimer quivers on a pinched torus and a genus 2 surface are shown below. These are some examples. And in these pictures, the vertices are all identified on around the polygon, and the opposite sides of the polygon are identified. So the first picture is is really a quiver that lives on a pinched torus, and the second example is a quiver that lives on a genus 2 surface. And so these are just some examples. So the unit cycles, let's see, can you see my mouse if I move this around? I don't know. But these little cycles here are the unit cycles, and notice that the arrows go in these little cycles. And just from this definition, we just need each of these little, there can't be any holes or anything within the unit cycles, but all these little cycles are the unit cycles. Okay, a dimer algebra of Q is the quotient A of the path algebra mod, the ideal generated by the difference of paths P minus Q, such as A, where PA and QA are unit cycles. So here's another example of a dimer quiver. This one is on a torus. And so in this picture here, all the 2's are the same vertex, the 1's are the same vertex, and this arrow on the left and the arrow on the right are the same arrows, and the arrow here on the top from 2 to 1 is the same as the arrow here on the bottom, 2 to 1, and similarly for going from this way, from 2 to 1. Okay, so what the relations are telling us is that, for example, this blue path P here is equal to this purple path Q, because we have this arrow A, and PA is a unit cycle and QA is a unit cycle. Okay, so these are dimer algebras. That's all there is to the definition. But now we'll look a little bit at the history of where these come from. Okay, so in 1980, Rota, Sagan, and Stein came up with the idea for a new kind of derivative for non-commutative algebras called a cyclic derivative. Then in 2000, motivated by string theory, David Berenstein, together with Vishnu Jujala and Robert Ley, applied this derivative to path algebras. So the idea is, so let Q be a quiver, and the cyclic derivative with respect to an arrow B is a K-homomorphism from the path algebra of Q to the path algebra of Q, defined on paths by what you do is you take a path, say, consisting of arrows A1 through AN, and then you cycle the path around, and you remove if the leftmost arrow is the one you're taking the derivative with respect to, you remove that arrow, and otherwise in that cyclic permutation, it's 0. And so you sum over all these cyclic permutations of the path. And of course, if it's not a cycle, then these will be killed off just by the path algebra relations. So, and then you extend this k-linearly to the whole path algebra. Okay, so for example, consider the one loop quiver. So just one vertex and one loop called the loop X. Then the partial derivative, or sorry, the derivative of, say, x to the n with respect to x turns out to just be n times x to the n minus 1. We were the usual derivative from this cyclic derivative. So Berenstein then introduced the superpotential algebra, which is the path algebra modulo. You have this fixed element of your path algebra called the superpotential, and you take a derivative, a partial derivative with respect to each arrow in the quiver. And so this is a superpotential algebra. And just a side note, so I put side notes in purple and in smaller font for the slides, but just the relations, these are actually classical Euler-Lagrange equations of motion from a particular Lagrangian, where W is part of the potential in this Lagrangian, and the arrows are fields on an affine patch of the compact real dimensions or 3 complex dimensions of space-time. So this is just a physics background as a side note. And the affine patch is actually the representation space of the superpotential algebra for a fixed dimension vector. And the dimension vector is called ranks of the gauge groups. Okay, but this is a side note for physics motivation. Okay, then in 2002, Berenstein and Douglas wrote down the standard projective resolution that would become the underlying idea for Calabi-Yau algebras. And I have it here for reference, but I won't go over this projective resolution. But you have this projective resolution for each vertex simple A module. So Berenstein conjectured that there's a pairing between the generators, so the arrows, and the relations. These algebras should have global dimension 3 in good cases, and otherwise 0, 1, or infinity. And if the global dimension is 3, then the center should be a 3-dimensional constant singularity. And some examples that we already know were like Sklejanin algebras for non-commutative algebraic geometry. Okay, so a few years later, mathematicians became interested in Berenstein's creation and renamed them Jacobian algebras. So here's a picture of David Berenstein on the left. Yeah, these are where superpotential algebras or Jacobian algebras came from. And then the other people involved. So Robert Ley and then in 2005, oh shoot, I can't. So there's a thing blocking my. So Ami Hanani and Christian Kenaway took dimers from statistical mechanics and combinatorics and placed them in the context of brain tilings and introduced a superpotential that's shown here. So it's the sum of the clockwise unit cycles minus the sum of the counterclockwise unit cycles up to cyclic permutation. So here's a picture of Ami Hanani and Christian Kenaway. And they use torque geometry and dimer combinatorics that we'll get to later called perfect matchings. And using these tools, they determine the representation space of the superpotential algebras with dimension vector all ones. Dimer algebras were thus born as the superpotential algebras of Hanani and Kenaway's dimer quivers. And indeed, recall our example of a dimer quiver on a torus. Then here's the superpotential, and remember, it's just up to cyclic equivalence. So here's the 2 unit cycles up to cyclic equivalence. There's just 2. And we can write this as PA and QA, and therefore we have that the difference of these, the blue path and the purple path, P and Q, is just the partial derivative with respect to A of these 2 unit cycles, AP and AQ. And so that we can see, and then this is just with respect to 1 arrow, but there's 4 arrows in the quiver, so you need to take the derivative with respect to each of the 4 arrows. And that gives you the relations. So tomorrow we'll look at this example in more detail and find the center of this algebra explicitly to see how these ideas work. Okay, so the first property of dimer algebras that we'll look at is cancellativity. So 2 paths P and Q in a dimer algebra A are said to form a non-cancellative pair if P is not equal to Q in the dimer algebra, and there is a path R such that RP equals RQ and the product is non-zero, or PR equals QR and that product is non-zero. If such a pair exists, then A and Q are called non-cancellative, otherwise they are cancellative. So it's just we can cancel paths when we can, in this, we can cancel the R's and say, if RP equals RQ, then P equals Q. So here's some examples of non-cancellative dimer algebras on a torus. So in each of these cases, these are all on a torus, and the vertices with the same label are identified as the same vertex in the quiver. So the first one looks just like the one I had up before, but now there's 2 arrows here in the middle instead of 1. And here's just 2 other examples. We'll come back to these later. So for example, consider the one that I showed on the left. The paths P and Q are not equal in this case because there's 2 arrows there, A and B, instead of just 1 arrow. Although if we put in the B, say, so we have BP equals BQ, then those will be equal because there's an A that completes them to be unit cycles. And so therefore, we can see right away that this is non-cancellative. This is a simpler example. The other 2 examples, to really see these non-cancellative pairs of paths, you need to draw more than 1 fundamental domain. So they're more involved to find the non-cancellative paths. But in this example, it's real straightforward. So 2006 to around 2012, many mathematicians began studying cancellative dimer algebras on the torus to see if Berenstein's conjectures held for these algebras. And the following theorem was kind of the main result that came out of all this work. Don't worry if you're not familiar with the words I'm going to use. I'll talk about non-commutative Crepin resolutions tomorrow and give definitions for these, but basically what the theorem is saying is that these algebras, if they're cancellative and on a torus, have very nice algebraic and homological properties. So let A be a cancelative dimer algebra on a torus, and let M be the maximal ideal at the origin of its center, C. Then the localization at that maximal ideal of the dimer algebra is a non-commutative Crepant resolution, whatever this means. So it has these nice homological properties of global dimension 3. Is a Beil algebra, and its center is a 3-dimensional normal toric-Ornstein domain. So it was found, yes, Bernstein's conjectures indeed held up for these algebras. But there was a lot of activity at this time with different people working on this question. However, cancellativity and the surface being flat, so a torus is a flat surface, its curvature is 0. So these were essential in all of the results. In fact, all of the nice properties disappear if the dimer algebra is not cancellative or on a higher genus surface. Furthermore, almost all dimer algebras on a torus are non-cancellative. So the ones that are cancellative are very rare among all the dimer algebras you could have on a torus. And from a physics perspective, cancellative and non-cancellative dimer algebras are on an equal footing. So they're equally good in M theory. And non-cancellative dimer algebras correspond to physically allowed unstable vacuum states. So they're physically allowed, they're just unstable. So they would quickly decay to whatever this means, to a cancellative one. So there are therefore two directions to explore. One is non-cancellative dimer algebras on a torus, and the other is dimer algebras on higher genus surfaces or surfaces with boundary, things like this. The second property that's kind of a main property of dimer algebras are what are called perfect matchings. And this is where the dimers came from, was looking at perfect matchings. A perfect matching of a dimer quiver is a set of arrows, and I'll use a variable x because these perfect matchings will become variables in a polynomial. But so we have a perfect matching is a set of arrows x such that each unit cycle contains precisely one arrow in x. And a perfect matching x is called simple if if q, the quiver, minus the perfect matching contains a cycle that passes through each vertex of q. So stated in terms of representation theory, the q minus x supports a simple KQ module of dimension vector O1s. So they're called simple because so if you can make a cycle that passes through every vertex and comes back to where you started, supported on q minus x, then that's the same as saying we can have a simple module of dimension vector O1s supported on q minus x. And we denote by P, script P and script S, the set of perfect and simple matchings of Q. And one side note is that we always assume that each arrow is contained in some perfect matching, and this is called non-degenerate. So it's just kind of, yeah, an assumption. You always assume each arrow is in some perfect matching. Okay, so here is an example. This was the quiver we looked at the beginning. This is a dimer quiver on a genus 2 surface. Again, we identify the opposite sides of the octagon, and so you glue those together, and you identify all the vertices around the polygon. And so this gives you a genus 2 surface. And these are there's 9 simple matchings. So you can work out what all of the simple matchings are, and in this case, these are the 9 simple matchings. We'll come back to this example again tomorrow, but this is just to show concretely what the simple matchings look like. And I've labeled them with variables, so there's x1 through x4, y1 through y4, and z1 through z4 for a reason that will become clear in a little bit. So the perfect matchings of a dimer algebra are closely related to its representation theory. So if you consider a representation of A of dimension vector all ones, such that some arrow is represented by 0, then there's a perfect matching such that each arrow in that perfect matching is also represented by 0. So the perfect matchings are really telling you about the representations that are possible of your algebra. So in the following, we'll construct a new type of algebra using perfect matchings in order to generalize cancellative dimer algebras on a torus, the higher genus surfaces for the non-cancellative case. So these, the new algebras, we'll call them core algebras, and consider a polynomial ring generated by the perfect matchings P of Q. So you have a variable in your polynomial ring for each perfect matching. And we'll label each arrow by a monomial, so call the arrow A, we'll put an A bar for a monomial in this polynomial ring, where if A is contained in the perfect matching X, then X will divide the monomial representing A. So this right here is the connection between, so yeah, if the arrow is contained in the perfect matching X, then X divides its monomial. We can then label a path P consisting of a bunch of arrows by just the product of the monomials for each arrow. And we define the Gore algebra of Q to be the quiver algebra, where two paths with coincident tails and coincident heads are declared to be equal if they have the same monomial labeling. So this is the Gore algebra. So it's really based on the perfect matchings. So the relations all come from the perfect matchings. Okay, and here's another way you could state this more succinctly is denote by EIJ the n by n matrix with the 1 in the IJ slot and zeros elsewhere. And so consider the algebra homomorphism eta from the path algebra to this matrix ring over the polynomial ring generated by the perfect matchings. And then we can define on the vertices I just gets sent to the, so eta of EI, the vertex EI gets sent to EII, so the diagonal matrix. And the arrows at A get sent, it's just putting that monomial for that arrow into the right place in the matrix, given by its head and tail. So when we extend multiplicatively and k-linearly to the path algebra. And the Gore algebra then is the quotient of the path algebra modulo the kernel of this algebra homomorphism. And so note that for a path P, eta of P is just a monomial times this matrix with a 1 in one slot and zeros everywhere else. A Gore algebra is then the quotient of a dimer algebra because the dimer algebra ideal, the ideal of relations for a dimer algebra is contained in the kernel of eta. So to see this, you just take if PA and QA are unit cycles with A an arrow, then eta of P will equal eta of Q. So it's clear to see this. And for the remainder of this talk and the next talk, we will primarily focus on dimer quivers on a torus. So the first thing you could say is the dimer algebra ever equal to the Gore algebra? And the answer is yes. And this will be precisely when A is cancelative. So we have So let Q be a dimer quiver on a torus, and let A be its dimer algebra and lambda its score algebra. Then the following are equivalent. 1, A is equal to lambda. A is cancelative. A is Noetherian. The center of A is Noetherian. A is a finitely generated Z module. And the last one is each arrow of Q is contained in a simple matching. So that is, each arrow annihilates a simple module of dimension vector all ones. So furthermore, these conditions are also all equivalent if we replace 3, 4, and 5 with lambda instead of A. So we have this connection between saying lambda is A is equal to its score algebra, A is cancelative, and A is Noetherian. So first, if we look at the first 3 of these equivalences, this comes from this theorem where if Q is a dimer quiver on a torus, then, and this only holds on a torus, not on higher genus surfaces. But in the torus case, lambda is equal to the quotient of A, the dimer algebra, by all the differences of pairs of non-cancellative, the difference of paths that are non-cancellative pairs. So what this means is A is equal to lambda on a torus if and only if A is cancellative. But on higher genus surfaces, this won't hold up. So thus the relations in any Gore algebra on a torus are simply homotopy relations on the paths in the quiver. So for any Gore algebra, the relations that you get from the perfect matchings are really homotopy relations in the paths. Well, what happened in the higher genus case is that it will also not just identify homotopic paths, but homologous paths. But on the torus, this doesn't happen. So from the previous theorem, the relations in the dimer algebra are only homotopy relations if the algebra is Noetherian. And otherwise, they're not. Okay, and now let's also look at the equivalence between 6 and 2. 6 was that the simple matchings, or each arrow is contained in a simple matching, if and only if A is cancellative, the dimer algebra is cancellative. So recall that non-cancellative dimer algebras on a torus that we looked at before, and the arrows in red are all each not contained in a simple matching. So the arrows in red do not annihilate any simple A module of dimension vector all ones. Equivalently, they do not annihilate any simple lambda module of maximal K dimension. So this will be the natural thing with the Gore algebras, because this is a real special dimension vector when you have just ones, because it's the dimension vector for the simples of maximal K dimension. And so yeah, these arrows drawn in red are not contained in any simple matching. And the one on the left is the easiest to see. So the one and the middle one and the right one are yeah, you have to do more work to see that this is true. But the one on the left, you can see right away, well, if you have dimension vector all ones, you can't, if the 2 red arrows are, you have zeros representing those arrows, you can't get to that vertex sitting between them. So you can't have any simple module where these two, either one of these arrows is 0. So the top one or the bottom one. Because remember, for it to be a simple module or simple representation, you need to be able to get from any vertex to any other vertex and back. And you can't do that in this case if either of the red arrows is 0. Okay, so now we'll look at some combinatorial characterizations of Noetherianity. So Dufin in 1968 and Mercat in 2001 made the following definition. A dimer quiver has an isoradial embedding if Q can be drawn so that the vertices of each unit cycle lie on a circle of radius 1. Then later, I think this was around 2000 or 2002, Kenyon and Schlenker came up with the definition for what are called zigzag paths. And these will also come back on Friday when we talk about cluster algebras, because these correspond to strands in strand diagrams and with Posnikov's definition of strands. So a path, A1, A2 to AN, in a dimer quiver with each AI an arrow is a zigzag path if AI plus 1 is a subpath of a clockwise, respectively counterclockwise, unit cycle whenever I is even, respectively odd. So these definitions were originally stated in terms of the dual graph to a dimer quiver, which is a bipartite graph that is embedded in a surface. A bipartite graph is a graph whose vertices form a disjoint union, say V1 and V2, such that each edge connects a vertex in V1 with a vertex in V2. And I'll give examples of this on Friday, but the vertices in V1 in this dual graph sit inside the clockwise unit cycles, and the vertices in V2 sit inside the counterclockwise unit cycles. But we'll see this more on Friday. But these definitions were originally given in terms of this bipartite graph. Okay. So in 2004, Kenyon and Schlenker proved the following. A dimer quiver on a torus has an isoradial embedding if and only if the following holds. 1, each zigzag path is a simple closed curve, and 2, the lifts of 2 zigzag paths to the universal cover are 2, because we're on a torus, intersect in at most 1 arrow. So zigzag paths, therefore, play the role of straight lines in the quiver. So they're as straight as possible in the quivers. And then, along with all the activity that came showing that cancel-to dimer algebras on a torus were Calabi-Yau algebras and non-commutative Crepin resolutions. So they have these nice homological and algebraic properties, whatever these words mean. There was also a lot of activity in showing different equivalent, there were called consistency conditions, or things equivalent to being cancelative. And there was also a lot of activity in the physics side at the same time showing that there were many different ways of showing what equivalent combinatorial conditions for cancellativity. So the people involved, I think the history is a little bit complicated. So Moscovoy and Rennecke came up with 2 conditions that were equivalent to these combinatorial conditions. Then Ben Davison found that the second condition was followed from the first, and Ishii and Ueda had similar conditions, and so did Buckland. So there were various people working on the same problem. And what was found was that if Q is a dimer quiver on a torus, then the following are equivalent. A is the dimer algebra of the quiver is cancelative if and only if Q admits an isoradial embedding. And so from the theorem of Kenyon and Schlenker, then it comes that the zigzag paths on Q, if we have these zigzag paths that really act like straight lines, so they, in the cover, they just intersect once, or they're parallel and they never intersect, then we'll know that A is cancelative. And so there was there was a lot of activity to show these equivalent conditions for cancellativity and isoradial embeddings. They went by other names too in the literature, if you see like rhombic tilings and things like this, but they all come down to the same. It's just another way of stating these same things. So here's two examples of dimer algebras on a torus. And so it's clear that the following dimer quivers on a torus admit isoradial embeddings, because in these pictures you can draw I don't know if you can see my mouse, but you can draw a circle around each of the unit cycles that has the so length radius. So you can say radius 1. And so since a unit cycle can be drawn around each grid square and thus around each unit cycle. And again, so the vertices with the labeled with the same, so there's 8 and 8, those are the same vertex, the 6 and the 6, and so on. And the arrows, so like this arrow here from 8 to 6 is identified with this arrow from 8 to 6. So whenever you see these are just drawn in a fundamental domain of the surface. One difference between these is that at the bottom, there's an arrow from 8 to 1 that gets moved over here from 8 to 1. So it's, but it still sits on the torus. So, but because you can just see right away from the last result that these have isoradial embeddings, and so these algebras will be cancellative in the theory. And you can check also, each arrow will say annihilate a simple module of dimension vector all ones. So all of the things work together very nicely. So putting the theorems together, we have that a Gore or dimer algebra on a torus is Noetherian if and only if its quiver admits an isoradial embedding. So kind of the magic of these algebras is that you have this algebraic property, like saying the algebra is Noetherian, that is completely equivalent to some topological or combinatorial property that wouldn't look like it would have anything to do with an algebra being Noetherian. So it makes a very beautiful picture. And so I actually, this was my last slide. So I went, I think I went quicker to the beginning, the problem with slides. But tomorrow we'll talk about the centers of these algebras. And so we need both, well, we want to look at both the centers of the non-Noetherian one. So from that theorem, the centers will be non-Noetherian also. So how do we talk about the geometry of these algebras? And then also what non-commutative resolutions are. So, and we'll work through an example where we see explicitly how you find the centers of these algebras. It's not a mysterious thing, but just to have our hands on concretely how all of this works. Okay, so yeah, I'll keep talking about this tomorrow.
Thank you very much for this very nice lecture. Are there any questions, because we have a bit of time? Yes? Can you say do you want to come here? Yeah.
Anthony,
do you want to come here and in front of the camera, or is there a camera?
Here, I can mute mine while you talk so it doesn't echo, maybe that.
Try again.
Can you hear me now?
It's a bit quiet, but I think.
Just a second, we're trying to use the microphone.
Okay, should I mute myself? I don't know if.
Or you come here and speak here.
Okay. Okay, is this working?
No. I don't know. It was working just a minute ago. Try again.
Can you hear me?
Yeah.
Ah, okay, great. Okay, so my question was why was there so much focus on the torus, historically, on the torus case?
Sorry. This is a great question. Yeah, okay, so the reason that physicists first were interested in the torus, yeah, so it has to do with the number 3. So in string theory, there's supposed to be these 10, space-time is supposed to be 10-dimensional. We don't see 6 of these dimensions, or these curled up compactified small dimensions. And so what the Daimer algebra, the geometry of the Daimer algebra is telling you is the geometry of these extra 6 dimensions, but in physics you're over C, so it's 3 complex dimensions. So 6 real dimensions or 3 complex dimensions. Now you want you want to have so to have these 6 extra dimensions or 3 complex dimensions, you want the center of these algebras, which in the cancellation case, of course, coincides with the representation space of dimension vector all ones. So you want that this geometry, you want it to be 3 complex dimensional. And so on a torus, it has to do with the pi1 of the torus. So you can go around the torus this way, or you can go around this way. And then there's also the unit cycle, which is the contractible cycle, but in the Daimer case, you can't actually contract it. So you have 3 kind of independent directions you can go on a torus. So you would have 2, but because of the unit cycles aren't really contractible, it gives you 3, and 3 is the number that you want, because so this will end up having the center that has dimension 3. So this was the original reason to put them on the torus, was so you get the right dimension for the geometry. And also, I mean, the number 3 was kind of this magical number, because also having this pairing between generators and relations, by Serre duality, it looks like the global dimension should be 3. And so again, then the global dimension would coincide with the crawl dimension of the center, and this is what you want for non-commutative resolution. So this was the reason that they were put on a torus, was so you get the center that has crawl dimension equal to 3 and equal to the global dimension, which you get from the Serre duality from the generators and relations, pairing them up together like this. So this was the idea. Yeah. Is this okay?
Yes. Yeah, it did answer the question. Thank you very much. And now we're supposed to have the tea break for 20 minutes. So let's thank Charlie again.